this computer. Okay, so we have the following questions on question 1. They're saying define the following terms: the union of an indexed family of sets. Then we have the intersection of an indexed family of sets. Okay, so before you even define the union of an indexed family of sets, you have to know what the indexed family of set is, right? Okay, then you can now know what the union is. Okay, so let me just try to define what first the indexed family of sets is, and then we can go on to the union and the intersection. Okay, so if I go to my board here, okay, I would say an index family of set is just a collection of sets. Okay, an indexed family, okay, index family of sets, okay, is a collection a collection of sets. It's a collection of sets where each set, okay, collection of sets where each set is associated, where each set is associated, or just write ASS, short form, associated with an index. Okay, with an index, or when we say index, we mean, in simple terms, we mean a label, okay? So an index, a family of sets, is just a collection of sets where each set in that family, okay, is associated with an index or a label. Okay, so what do I mean about when I say that? Okay, so for example, if you come at Onza, right? Okay, we are all students at Onza. Okay, so meaning we belong to that family of the Onza family, right? But each one of us has the student ID number, right? Which distinguishes him or her from the other person, right? Okay, so that's what we mean. Like, it's a set, collection of sets where each set is associated with an index or a label. Meaning to identify a certain set, we have to know its label, or to identify a certain student in the university setup, we have to know their student number, right? Yeah, so that student number is the index or the label for that student. So it's the same thing when you come to sets, okay? You have an index that will represent that set. So for example, if I get the alphabet, okay? If I get the alphabet, I know that from the alphabet, I have letters A all the way up to what? To Z, okay? So all these letters there, A, B, C, D, all the way up to Z, those are index. For you to know that this is A, you come on A. For you to know that this is Z, you come on Z, okay? So they are the labels in that, within that alphabet, okay? So now when they say an index family of sets, it just simply means that we have, okay, these sets we can call AI, okay, such that this I belongs to the indexing set. Okay, okay, to the indexing set, which is represented by a capital letter I. Okay, so these small i's here, they belong to this big letter I, okay? And then for each of these i's, we have a set which we say set AI, okay? So this here will represent a family or index family of sets. Okay, so the index family of set is represented by this. Okay, so that now we know what an index family of set is, we can now go on and define the union. Okay, so the first question there, will define the union of an index family of set. Okay, so we are saying union. Okay, so we know that the union for an index family of set is just defined by the union, okay, of all these AIs, okay, where I is a member of the indexing set, which is I, the capital letter I, right? Okay, so this would be equals to an element A, okay, such that that element A is a member of these AIs, okay, for some okay, for some I in that indexing set we are calling I, okay? Okay, for some, okay, so for some I, small letter I, that are members of the big letter I, which is the indexing set, then you put closed brackets, okay? So this is the definition of the union for this indexed family of sets. Okay, and then for the intersection, it's just going to be the same thing, but we're just going to change the language. Okay, so we know that if for example I have set A and B, right? If I have set A and B, it means that if I take the union of set A and B, I'm going to get elements that are either in set A only and set B only, and then I combine them. Or I can get elements that are both in A and B, I can also combine them, right? Okay, so when we say for some I here, it means this A might not necessarily be in all these AI, but just for some AI, okay, because it's the union. So we can get from this set, and then we combine, right? Okay, and then when we talk about intersection now, okay, when we talk about intersection here, it means we are getting members that are common to all the sets, because intersections, it requires that if I have A intersection B like that, okay, then the elements that should be here should always be found in A and also in B. That's what the intersection demands. So if we want now to define the intersection family of sets, of indexed sets, okay, you say that it's the intersection of all these AIs such that this small I is a member of the capital letter I, the indexing set, which will be equals to, okay, a set where you have A as your member such that this A is, okay, a member of the AI, okay, and now here, that's where you have the difference. So here we said for some, meaning this A is not necessarily in all these AIs, okay? But for the intersection, it's a must that this A here, okay, if it's a member of this, okay, then all these I's here, they should contain that A, right? Okay, so A is such that A is a member of AI for O. Okay, here you say for all I that are members of the indexing set I. Okay, so this is the definition. Okay, this is the definition. So where it differs is that the union you can get from one, and then you combine with the other members in the other sets. Okay, then for the intersection, it means if you have an element A here that is a member of this AI, then this A should be a member of all the AIs that I can have, okay? So that's why here we're saying for all I is a member of the intersection set I. Okay, so I don't know if you have any questions, distributions, I don't know.
I understand.
Okay. Okay, so we move on to the next question. So we've defined the union of an index family of sets, and then the intersection of an index family of set we've also defined, okay? So now that we have defined, they are asking us now to prove these two theorems here, okay? They're asking us to prove if the union, okay, the complement of the union of all these AIs is the same as the intersection of all the complements, right? Okay, so we know that these are just De Morgan's law, but that are a bit advanced, right? Okay. So if I come here, we know that De Morgan's law just states these two. If I have A union B, and then I have an intersection outside, okay, then it means that this is the same as A complement intersection B complement. Okay, and then if I have A intersection B complement, okay, it means that I have A complement union B complement. Okay, so if you know how to prove this De Morgan's law, and you also know how to prove that De Morgan's law, we are going to be using the same basic knowledge to prove whatever question that we have there, okay? Because the steps, they're just similar. So we follow whatever we follow in proving this, and then we can be able to prove those for families, okay? We can also be able to prove for families, okay? So they're saying, let AI, so that I is a member of the indexing set I, be an index family of subsets of A, then they're saying prove the following. Okay. So we know that to prove that a certain set, for example, let's say A is equals to B, okay? So to prove, we must satisfy two conditions. We must show that A is a subset of B, okay? And we must show that what? B is a subset of A, okay? So we are proving both directions. Don't just prove one direction, then you stop. No, we have to prove that A is a subset of B and B is a subset of A. If we are claiming that A and B are equal, right? So that's the rule in set theory. If you claim that A and B are equal, then it means that A should be a subset of B and B should be a subset of A. Okay, so now let's go to our question. So the first question there, so we are solving B now. One, they're saying prove this De Morgan's law. They're saying the union of I is a member of the indexing set I, okay, for all these A's, and then we take its complement is the same as the intersection of these I's, okay, for all the A complement I there, like that. Okay? So this is the first De Morgan's law. So how do we prove this? Okay, so for you to prove, you have to know how the complement rule works, and you have to know how the union works and how the intersection works, right? Okay, so let's try, okay? So if we want to prove that this is equal to this, then we must show that this is a subset of this, and then again, that is a subset of this, okay? So the first point is always to suppose, or you claim, okay? So suppose that X is a member of this set that we have here, okay? Suppose that X is a member of this, U, I, then we have I there, then AI, this should be I, okay? And complement, okay? Then we know by definition of a complement that that X will not be a member of this same guy here without the complement, right? So, meaning to say if X is a member of A complement, right? Then we know that A, how am I saying A? This is A. If X is not a member of, is a member of A complement, then X should not be a member of what? A. We know this theorem, right? So this is the same theorem that we are going to use. So let's use it. Okay, so here they're saying, suppose that X is a member of this, okay? Then by definition, okay? So then by definition, okay? So I'll just write DF. So by definition, then X will not be a member, okay? Will not be a member of this actual set because it's a member of its complement. So it can be in both the complement and the actual set, no, okay? So suppose that X is a member of this, then it means that this X is not a member of the actual set there. You've seen here we've removed the complement there, right? Okay. Okay, so what does this mean? Okay, so this means that this X is not a member of any of these AIs, okay, because it's not in the union. Okay, so it means that X will not be a member of any of these I's. Okay, so you write that X is not a member of these AIs for O. Okay, for O, I is a member of the indexing set big letter I. Okay, so why are we saying this? Okay, because we said union, we can just get, if X is a member of one set, then it means it's in the union. Okay, but here they're saying X is not in the union of this. So it means that X is not a member of all these AIs for all the small i's in this capital letter I. Yeah, so that's what it means. Okay, so by this now, we can conclude that since X, okay, since X is not a member of all the AIs, okay, then X will actually be a member, okay, of this AI for all I in I, right? Okay, if X is not in this, then it means X is in, I'm supposed to write complement here, yeah. So if X is not in the AI there, okay, then it means this X is in the complement for all I in the capital letter I, okay? And this simply means that this X is just a member of, since the X is in these guys for O. So remember the definition for the intersection here. Where is the definition for the intersection? For intersection, we said this A should be a member of this for O, okay? For O. So here, when we come back where we are here, we can see that X is a member of the A complement I for O, okay? So it means this X just simply a member of the intersection for for all the I's in I of the AI complement like that, right? Okay, so this shows that okay, so this shows that, okay, you AI complement is actually a subset of this guy here, because we started with this and then we ended up with this. Okay, so it means it's a subset of the N AI or the AIs in the A complement. Okay. Okay, any questions? Do you have any questions?
I have a question on the first
Yes.
part.
Which part?
Here, the proof is for the union part, eh?
Okay, just wait a minute, I changed my color. Here?
Yes. So like the proof that you have written is for the union part.
Yes, it's for the union part. Is to prove that this guy here is a subset of this guy.
Then where you say, suppose X is in this union, the complement part of the union, then
Yes.
by definition, X is not in the on the part that isn't complement. Yeah.
This part here.
This this means that X is not in AI for all I in the index.
Yes.
Now here, while we were defining the union and the intersection, didn't you say that the union for the union was supposed to say for some?
Yes. So in the definition for the union, you're supposed to say some. But remember, for the union, okay, if we are getting the union, it can be those elements are found in both, or they can just be found in one. Remember, right? For the union.
Yes.
You remember?
Yes.
Yes. So meaning for the union, by definition, if you are defining it in that definition, you are supposed to write for some. But it doesn't make it wrong when we say, like for example here, what we say it here for all here. No, it doesn't. Yeah, because if it was in one of these AIs, then this X would have been in this union. But this X is not in all of these, right? So it means that the X is not a member.
Okay.
Okay, so what we've done here, we've just proved one part. Okay, we've just proved that this is a subset of this. Then we have to show again that this is a subset of this. Then our proof will be complete for the first one, right? Okay. Okay, so this is our conclusion here. We've shown that this guy here is a subset of this. So now how do we show that this is a subset of this? Okay, so you say conversely, suppose that, okay, so conversely, I don't know if this is the correct spelling. Okay, so suppose that X is a member of intersection I, and then you have AI complement there. Okay, so suppose that X is in that, okay, and then by definition, just write DEF. So by definition, what does this mean? Okay, so what does it mean if X is a member of the intersection of all the complements, right? So it means that X is not a member of the actual set, right? Okay, so X is not a member of the actual set. This is in the complement. So X is not a member of this. That's what it means, right? Okay, and then by the intersection definition, we know that if X is not a member of this intersection, right? Then it means that X is not a member, of this AI or other I's in the indexing set. We know that this is true, right? Okay. Okay, and then from here, thus, we can conclude, we can say thus, X is a member, okay, of a I complement for O. Okay, for O, here I forgot to put the weights for O. So you can put here for O, I in the indexing set, even here for O, I in the indexing set. Okay, so we know that this here can turn into the union, right? Because we are saying X is a member of the complement of AI for all the I's in the indexing set, okay? So meaning that X is actually a member of the union of all these complements of the indexing set, right? So you're going to say the union of I, which is a member of I for all these complements of the indexing set, like that. Okay, so from here we see that what we had at first, which was the intersection I of all the AI complement, is actually a subset of what we have here. Okay, so I is a member of I like that for the complement. Okay. So you can also label these equations so that you can refer to them later easier. So we can say, was this one? We can say this is our equation 1, okay? And then where is this? We can say that this is our equation 2. So since we've shown that the left is a subset of the right and the right is a subset of the left, okay? So we can conclude then that combining, okay? Combining 1 and 2, okay? Combining 1 and these 2, it means we get the union of this I, the member of the I, then AI complement is actually equals to the intersection of I is a member of the I complement like that, right? Okay, and then you can even write hence proved, because you've proved both directions. You proved both directions, so you can say hence proved. Okay, are we okay?
Yes.
Okay, so we've done the first part. Let's do the second part. Okay, so let's do the second part. So we've done this one. Let us not now do this one. Okay. Okay. Okay, so here, because we are starting with union, okay, we are starting with union going to the intersection like that. It means the prominent definition that we have to know is the one for the union, okay? But here we are starting from the intersection and then going to the union, meaning the most important definition that we must have is the one for the intersection. So let's do it. Okay. Okay. Okay, so this is number 2. We are proving that the intersection of I for all these to my I's, AI complement is actually equals to the union of all these I's in the indexing set for all the AI's complement like that. Okay, so it's similar. Okay, it's similar what we have. Okay, so the first step is always to suppose. So we want to show that this is a subset of this, and then later on, this is a subset of this. So we're going to say suppose, okay, suppose X is a member of this guy here, okay? Suppose X is a member of this. Then by definition, okay, so by def, X is not, okay, X is not a member of this set here that I'm writing now. Okay, so if X is a member of the intersection complement, okay, then by definition, the X is not a member of the actual set. That's what it means, right? Okay, and then if I go back to the definition for the intersection, right? We said if something is an intersection, right, then we demand that this X, this is a member of this, should be a member of all these I's, right? That's how we defined it. Okay, so if we have found here that X is not a member of this set here, which is the intersection, okay? If X is not a member of this set, which is the intersection, then what it actually means is that, okay? So we start with the simple stuff. It means that X is not a member of this AI, Okay. For, okay. Okay. So remember, for this X to be a member of this, when we demand that all the I's, okay, if this X is a member of this, we demand that the X should be a member of these I's for all the I in this set, right? Okay. But if X is not a member of this, okay, it is possible that X is a member of some of these AIs, but it's not just all. No wonder it's not in the intersection, because the intersection means that it's a member of all of them, right? Okay. So if it's not a member of them, then here we have to say for at least, okay, for at least one I in I, then this definition will not hold and to be true. Okay, so we're going to say for at least one I in I. Okay, if only one of them is not a member, then X will not be in the intersection. So if let me illustrate. If I have set A, set B, and set C, okay, for me to have A intersection B intersection C, it means that that member is in A, it's also in B, and it's also in what? In C, right? Okay. Then in the situation where I have a member that is not in the intersection of these three sets, it means that member, it can be in A, it can be in A, but it won't be in C, right? Or it can just be in A and it's not in B and it's not in C. Okay, that's where this at least is coming from. So if I have an element that is at least not in one of these three sets, then I'll say that that element is not a member of A intersection B and intersection C, right? Okay, so this is the concept what we are using here. Okay, so this is where the proof differs from the first one that we did. The rest, you will see, they will just be the same. So here we're saying if X is not a member of the intersection of the index family of sets, okay, then X is not a member of this AI for at least one I in I, okay? This is what it means. Yes, this is what it means. Okay, so thus, or it follows, I don't know the English that you want to use. Okay, we can use thus, X is not, okay, a member, is not a member of, what was I explaining? I'm confused. Okay, let me follow it for me. If X is not a member of this, okay, yes, this means that X is not a member of A for at least, okay, one I in this indexing set I. And then now I'm saying thus, okay, thus X, okay, so here I have to put a member then, because there it was not a member of, okay. So if X is not a member of AI, then X will definitely be a member of AI complement like that. Okay, a complement like that for at least. Okay, so we use the word at least in this proof for at least one okay, for at least one I in this I like that, right? So this is what it means. If X is not a member of AI for at least one I in I, then it means that this X is a member of the AI complement for at least one I in I. That's what it means, okay? And then from this now, we can conclude, okay, that hence, since it's a member of this for at least one of them, then we can conclude that it's in their union, right? Because union, you just get if it's in one of those sets, then it will be in the union. Okay, so you can conclude that thus X will be in their union of these complements here. So X will be in the union of all the i's in the indexing sets I, a complement I, like that. Okay. So this shows that whatever we have is a subset of whatever we have here. Okay, so I don't know if you have any questions there.
I understand.
You understand? Okay, that's good. Okay, so here we had this AI, and then complement is a subset of this. So U, I, member of I, a complement, like that. Okay, so we have shown that this is a subset of that. We can label this as our equation 1. Okay, and then we go to the other proof now. We want to show that this is a subset of this. Okay, so always we start with suppose. Don't forget to write the word conversely there. So suppose that X is a member of union I of this indexing set of the AI complement, like that. Okay, then by definition, so then by definition, okay, if this X is a member of the union of the complements, then this X definitely not a member of the actual sets, right? Of the union of the actual sets, like that. Okay, so if it's not the union of these, okay, then it means that what? It means that the X is not a member of the AI, okay, for at least, because this proof is, we are starting from the intersection to the union, so you say for at least one I in this indexing set I, right? Okay, so if this is not a member of this, then it means X is not a member. Here I'm supposed to write it's not a member. X is not a member of AI for at least, okay, for at least one of these, okay. Thus, we can convert this now to the what? To the intersection, right? We can convert this to the intersection, because if this one of these is not a member of this, then it means that X is actually a member of the AI complement. Okay. Are we supposed to use at least here or for O? Is it making sense? Yeah, on the intersection here on the definition here. So if we are saying X is not a member of this union here, okay, the union of all the AIs, and then we are saying X will not be a member of the AIs for at least one. Are we correct if we use for at least one? Let's brainstorm. If we use for at least one here.
Are we supposed to use for O?
For all, right?
Yes.
Yeah, I think for all. Because this is
At
union.
least part, yes, isn't at least part for the intersection?
Okay. All right. So I think here we're supposed to use for O, because here it's in the union. So union can't use at least. So okay, let's see if the proof will come out. Okay, so here we are going to say for O, the I is in I. Okay. Then since we have that, then it means that X will be a member of the AI complement for O, right? Yeah, this works. For O, the I in I. And if we have X is a member of a complement for all I in I, then it means we can turn it into the intersection, right? Because the intersection is said for O. Yes. Okay, so it means the X will just be a member of the intersection of the i's in the indexing set of the AI, and then complement outside there. Okay, so this shows that you no, I'm not supposed to say, okay, yeah. So it involves that the union of this or the AI complement there is actually a subset of this set here on top. So we are going to write N, okay, then AI complement like that. Okay, so now this makes sense. And then we can say that this is our number 2, okay? So if this is our number 2, we can now combine them. So combining, okay, combining 1 and 2, we get, okay, combining 1 and 2, we get that the intersection of this i's like that of the AI, and then we have a complement outside, is actually equal to the union of the i's in the indexing set of the I complement like that. Okay, then you can even write hence proved here. Okay, so is it okay?
Yes.
All right. Okay, so the next question now. Okay, so I've also answered this one. And then the next question is just about finding these actual unions, these actual intersections. Okay. So here we've been given a set which is 3 minus 4, 4n over n minus 1, okay, over 4 over n. And then they're saying this n is a member of the indexing set I, and that indexing set I has members starting from 2 all the way to infinity. Okay, and then they are saying what? They're saying find the intersection of all these subsets of this set, and then again they're saying find the union. Okay, so the easiest way is just to start substituting these numbers. You substitute 2 into this one, substitute 3, substitute 4, and then you plot the points that you're going to get on the number line, and then you see the pattern that you're going to get, right? I think that's the easiest, okay? I think that's the easiest. And then what can I say? Okay, let me not use that method. It may be difficult. So let's use the one for substituting. So we are going to put 2 here and see the coordinate that we are going to get, because this is just a coordinate, okay, that we can plot. Not a coordinate, actually, I'm saying an interval. So it's an interval that we can plot. So we'll be plotting the interval that we get. If we have that, we can have that, and then we see the pattern that they are forming, right? I think that's the easiest way. Okay, so let's try to do that. Okay, so the set that we have is Ln is equals to, we have an open brackets 3 minus 4n divided by, we have n minus 1, comma, 4 over n. And then we have a closed bracket here. Okay, and then the n values, we are given that they start. So 2, 3, 4, all the way up to infinity. So without even solving here, I can see that this number that I have here, as this n grows, it means this guy will be approaching 0, right? Yeah, will be approaching 0, because if I divide this number by a very large number, because I'm going to towards infinity, it will just be going towards 0, 0, 0. If I divide by a large number, it will be 0.11110000 something, right? Okay, and then I can see that this one here is just heading towards -1, okay? But let's prove it. So let's say we want to find n I1, hey, I2, because we are starting from 2. There's no 1 in this indexing set. So I2, it means that what? It means that we are going to put 2 wherever there's n there. So it will be 3 minus 2 minus 4, 2, I mean, divided by 2 minus 1, comma, then here it will be 4/2. Okay, so this will be equals to what? So you can simplify this. 4 multiplied by 2, it will give you what? 8, right? And then that 8 divided by 1, so it will just be 3 minus 8. So 3 minus 8. So make sure you go with your calculator in the test for your analysis. So this will be just be -5, and then on the other side you just have 2, right? Are you following?
Yes.
Okay, so this is for 2, and then let's try to put 3. You just see the pattern. So if this is 3 now minus 4 multiplied by 3 over 3 minus 1, comma, 4/3. Okay, so this is a closed bracket like that. So is equals to, so when you calculate this, it will be what? So this will be 4 multiplied by 3, which is 12, divided by 2, which will just be 4. It will be 4, right?
12 divided by 2.
Oh, it will be 6, I mean. Yeah, and then 3 minus 6 will just be minus 3.
Minus 3.
Okay, and then here is just 4 divided by 3. 4 divided by 3 is what? 0 point something something.
1 point something.
Okay, so 1 point, this will be 1.666666, right?
Yes.
Yeah, so you can just say 1.7 like that, then you put a closed bracket. Okay, you keep.
Can I correct you on something?
Yes.
On the 4 divided by 3, it's 1.333.
Oh, 1.33.
Yes.
Oh, yeah. Not, I thought it was a 20 there. So this would be 33333. But the remainder was 2. The remainder is 1, so it would be 3 years. So 1.333 until K. And then this would be I4, 3 minus, okay, this would be 4/4 minus 1, comma 4/4. So you can continue going. I don't know how many you can try, but at most maybe try 3 or 4. And then put a very big number to see what will happen. So here now it will be 16 divided by 3. 3 minus 16 divided by 3. What do you get there? Okay, so you get
5.3333.
5.333.
Yes.
Will it be a negative or positive? I think it should be a negative.
To be a negative.
Negative, right? Are you sure it's 5? Because this is 3 minus 16/3. 3 minus 16/3.
Check it.
No.
It should be negative.
Should be negative 2 point something, right? Negative 2.333.
It will be negative 2.333.
Yes, negative 2.33. And then on the other side, you just have 1. like that. Okay, so now let's jump the gap. Let's put maybe 500. We see what will happen. Okay, so it to be 3 minus 4, 500. So you can do this on your calculator, and then down there you have 500 minus 1. We'll see what will happen to this interval. So this will be 4 over 500. What are you getting?
It's -1.
Negative 1 point.
0.00.
Mm-hmm.
2.
Okay, 2.
0, 0.
0, 0.
4.
Okay, we can end there, and then we say comma. What is 4 over 500? It will be 0.000 something, right?
0.008.
Uh-huh. Okay, so what do we notice from here? Okay, so we can put it on the number line to see it, how it will look like. So if this is my number line like that, I'll say I have my 0 here. I can have my 1 there. I can have my 2. Even on the other side, I can have, we had -5 there, so -1, -2, -3 there, -4. I can have -5. And then I try to plot these points that I have there, right? And then we'll see what will happen to the intervals. So the first one is -5 to 2. Okay, so the 5 is not included, but the 2 is. So -5 all the way to 2. So the 2 is included, you put like that. And then the other one is what now? -3,
From
1.333, right?
Yes.
So -3, 1.333, it can be somewhere here, right? And then we plot the other one, it was
-2.33.
-2.33, so it can be somewhere here, all the way to what?
1.
All the way to 1? Yeah. So we
Yeah.
go at 1 here, we end at 1. What was the other one? It was -2 to what?
-1 point. No, it was -1.
-1?
Yes.
Are you sure? Oh, this one?
Yes.
Oh, okay. So -1.000 something.
Yes.
Okay. So since it's -1.007, so slightly just after -1. So we can have it somewhere there. And then it was going to 0 point something, right?
0.008.
Yeah, so 0 point. So it just means after the 0.8, somewhere like there, right? Okay.
Yeah.
Okay, let me draw that one properly. The last one. Okay, and I remember how both are both. Okay, so we are just saying slightly, just before the 1, and then 2, just after the 0, like that. Okay, so what we see is that whatever number that we'll get, okay, it will just be getting closer to this -1. Charm pencil, charm misbehave. Okay, so whatever number that we get, it will be getting closer to -1 from the left, and it will be getting closer to the 0 from the what? From the right. That's what you see. Yes. So from the right, you are getting closer to 0. From the left, you're getting closer to 1, right? But you will never reach -1. You will never reach 0, no matter how you try. Okay, so on your own, you should put a very big number there, like 1 million. You see, you will not reach the -1 and the 0. Okay, so this simply means that the intersection will just be between this -1 and 0, right?
Yes.
And then the union, since the union, we get everything. So it means the union will start from -5 to 2. Do you agree?
Yes.
Yes.
Now, how are we going to write the intervals in the intersection part?
For the intersection? Okay,
yes.
So this is how you write it. So you're going to say, therefore, my intersection here, the saying A for all the n's in this in is just equals to open interval -1, comma 0, open interval, close interval there with a curved bracket like that. Okay, because we know that
it's going to be open on 0.
Yes, it's going to be open because the 0 will never be met. You get? So
Why
it will,
is it
Why is it?
Why is it open on both numbers?
On both hands. Okay. So when we are coming here, right? If we are coming from the left here, we said the numbers will keep on getting closer to -1, right? But they will never be -1. Yes. Okay. So this is the curved brackets here because -1 is not included, but -1.0000 something is included, right?
Yeah.
And then when we are coming from the right like that, okay? I know in the actual question we had this and that. But according to this, what we are seeing on the number line is that when we are coming from the right here, we'll be getting closer and closer to 0, but we'll never reach 0 as well, right? Are you understanding it?
Yes.
Yes. So we'll just be getting closer and closer to 0, but we'll never reach the 0, right? So it means the intersection will just be between these two numbers here, but they will never reach -1. They will never reach 0. So immediately you go to something. It means the intersection will be no, not 0 point something. Like any number that is less than 0. It means it will be there in the intersection, right?
Yes.
Yeah, so no wonder here we're putting a curved here and also a curved there. So always look at how the number line is behaving. When you plot your point, always look at how the number line is behaving to judge the kind of brackets that you're going to put. Okay, but for the union, it will be very simple, right? So the union, you just get the end point. So the first one, we said it's from -5 there. So open -5, and then all the way to the 2 is included here. The 2 is included here. So it means that we actually put a curved, a square bracket like that. So these are our two answers there. Is it okay?
Yes.
Okay. Yeah, so I think for today that's okay. Then tomorrow we can do question 2, right?
All right.
All right. Have a blessed night.
Thank you.
You're welcome.